Good morning for day two. Welcome everybody who's online. Just before starting, I just wanted to say something about the host here, the CWI, where we are on the Science Park. It's the Dutch National Research Centre for Computing and Mathematics and Computer Science, actually. So as I said yesterday, it's the birthplace of the open internet in Europe. But it's been around for 75 years. Last year it celebrated its 75th anniversary. And you probably don't know about its history, but for instance, Edgar Dijkstra worked here for 10 years. He did his initial work. He learned to become a programmer here. He did his PhD here on the first Dutch, the design of the architecture of the first Dutch computer, the Arrow 1. And he also built the world's first Algol 60 compiler here. The director and his PhD mentor was Aad van Mijngaarden, and he was involved with both Algol 60 and Algol 68, which means that the word dereference actually comes from the CWI via Algol 60. If you want to know the story behind that, I'll tell you later. Python was developed here by Guido van Rossum. He and I worked together on a project on programming languages, and then he moved to a project designing an operating system, and he needed a programming language for that, so he designed Python based on the programming language we'd been working on before that. And in fact, many of today's cryptographic algorithms that get used were designed here by the mathematicians using that first programming language that we designed, because that had unbounded numbers, and so they could use that happily to design cryptographic algorithms. I'll finish my introduction with a picture of Guido van Rossum there in the middle. And that's me with him. They say it was a very good party. I don't remember it. So anyway, our first speaker today, he had a very nice story last night of how he came to be here. He just Googled for a declarative conference and found us and submitted, and we liked his stuff, and so he got accepted. So he's going to tell us today about declarative, axiomatic, and provable correct systems in Swift. Manuel.
My name is Manuel. Today I want to present what I've been working on pretty much during the pandemic. And what I think is what I actually call the declarative domain coding paradigm. Yeah, if the slides are not readable for the people who are on Zoom, I put them online at this address. I know that all of you are aware what declarative coding is, but I also have to think about my fellow mobile developers, as I come from iOS, and their declarative coding is still something that is widely not even heard of. Yeah, it describes what you want to achieve, rather, and not how. But I also like to say it is actually the way we talk is declarative, because we don't tell each other how to do things. We don't tell each other how to open the door, but to open a door. Actually, by far, most codes are actually declarative, and who knows why that is? Why do I make this statement that most codes are actually declarative in the world? Because of Excel. The scripting language inside of Excel is declarative, and that's the most used computer language in the world. I also would like to say, and that is something that I experienced very strongly while working on this kind of coding, that it's also a very high degree of alignment that I feel that I have with the compiler, and I think it's more brain-sized coding. Yeah, first I want to talk about simplicity versus complexity, and I have the next demo there. Xcode, no shenanigans now, please. It always needs a little bit to start up the simulator. So in the top, we see two simple pendulums on top of each other. And I will start it. And as we would expect, the motion is quite predictable, and we can infer from one pendulum's position where the other should be expected to be. But what happens if we introduce just one complexity? And here we see that we have the same setup here, but the pendulums are have one joint each. So let's see what happens in this case. So is now anything deductible from one pendulum to the other? Or, I mean, even for one pendulum, it's not able to predict the movement for more than just a few moments. So, and that is why simplicity matters, because even small amounts of complexities can already create a lot of complex behavior, as we would expect. And we cannot really deal with it. Before you all get hypnotized by it. Complexity leads to unpredictable behavior. Unpredictable behavior leads to errors. Most teams actually only now adding complexities. Often they are not even they even don't have neither the capabilities nor the mandate actually to reduce complexity. Yeah, which of course means they are stuck in a loop. And I myself in my career have seen teams not able to get out of this situation for more than years. So we need to truly embrace simplicity, and no one should expect to fight complexity with more complexities and that they win. I mean, it is the sustainable business model. If you produce the errors that you later will try to fix, you have a good job. Yeah, and of course, code is where bugs live. Excessive amounts of codes can or will contain excessive amounts of defects. The only solution against complexity is simplicity. And here I want to show how we can write systems more simpler. I also feel that I need to say that simple is not the same as easy. Often simple is actually quite hard. So easy is an experience that a person has. It depends on his background or their background, and what they have been exposed to, how much they are up for learning, all this. While simple describes a structure. Often we should use it in a comparative, something being simpler or more complex than anything else. I want to stress that immutable is actually more simple than mutability, even though many people might react to that now, and that's the difference to being easy. If you're not have been exposed to immutable programming, then you might find it hard. But structurally speaking, it is simple because it is simpler for the compiler, because the compiler does not need to maintain the codes to allow mutability. Immutability is simpler because it is simpler from the perspective of the compiler. Unidirectional flow of data is, of course, simpler than multi-directional flow. And here it's actually not the compiler for which it's simpler, but our own brains. Classes are inherently complex. We will come to classes back again, and therefore actually should not be found at the hearts of our systems, because the more central a complex structure is, the more influence it will have over the total system. Yeah, I call this the what I'm showing you today, the declarative domain paradigm. First of all, what is a paradigm? It's also not really, I'm not aware that there is a real definition for what a paradigm constitutes within our field. For me, it's the idea how to organize code with constraints. For example, the understanding that unconstrained jumps are complicated. I mean, especially, again, complicated for our brains. The compiler can eat this stuff for breakfast. Here to mention the paper "Go to Considered Harmful" often is today seen as a beginning of structured programming. And for object orientation and functional programming, I want to say that they both have identified global mutable state as a problem. And while OO hides the state from the global scene, but might keep it mutable, functional programming has global state, but it is immutable. So there's two different solutions to the same problem. So instead of classes, I actually use a partial application inside of my coding. Has anyone heard about partial application? I would have expected the older hands to go up, but yeah. Any reactions from Zoom about partial application? Okay. Yeah, so I use partial application. I will explain in a moment what that is. And behavior and intent are expressed as small chunks of data and are decoded by pattern matching. All the model and the state will be immutable. By the way, the pendulum example also is written in this style. It is the pendulums are immutable, and yeah, but I will come to the code also back later. So why not use classes? Yeah. I think classes are actually too powerful. They do too many things. I once wrote down all the kinds of interactions that you can interact with classes, and I think I came up with 8, and I'm not sure anymore how I did that. But yeah, stuff like, yeah, subclassing, adding new methods. That is all very complex, but maybe one of the biggest problems with classes are certainly that I think they are not good tools to share understanding with the compiler, because a lot what goes on in classes is actually inaccessible to compiler to understand what's going on. If I subclass functions or methods and I have to read nodes, subclassing nodes, to make sure that I subclass everything that is meant to be subclassed together, then that is the information that the compiler simply doesn't have. And yeah, it's not seen anywhere in the signatures. And yeah, therefore, classes do not help me to align myself with the compiler. The one thing that I actually need from them, that they work as a black box, and I mean, that's what they advertise for many decades now, they're actually quite bad, because I often need subclassing information beyond what the compiler knows. Which also leads that to a situation that we have a whole zoo by now for pattern. If you ditch classes from your system, you will simply don't need any or just one or very few patterns in your code. The thing is, I like patterns. They make me think that I work on codes like a clock maker was preparing clocks 100 years ago. But in the end, they are not what the customer asked for. And so if I just introduce them because I am used to them and I like them, then it's not the right motivation. They add again complexities, and we want simplicity. Yeah, classes promote unconstrained coding, where we actually want the opposite. And in civil engineering, in real-world engineering, we are yeah, real-world engineers are governed, let's say, by the laws of physics, while I believe that we as software engineers have to come up with our own physics, and yeah, classes are simply not very good to do that. Yeah, this is what I just said. Okay, partial application. Partial applied functions are functions that are executed and they return another function that I can keep around and use as often as I want. The outer functions body offers me the possibility to, like here in this example, keep state. So for example, as we reference the value variable, which is defined in the outer function scope, as we reference it in the inner function scope, it will be kept around after the function was executed. And now that, can I turn around and the microphone still works? Yay, improvement. So when I create an adder here and write it to the variable adder over here, and now I can call it with any parameter. So this will create a 5, and this will create a 6. So this state is kept in the value. So this is a function with side effects, which also means this is not functional programming. This is not compatible with functional programming. You will sometimes find partial application mentioned as the ultimate pattern in functional programming. Functional programming doesn't need pattern. Yeah, those people simply have not understood what functional programming is about, and they have recreated a form of probably object orientation in functional coding. And that is exactly what we are doing here. It's just that I don't call it functional programming, so then I can use it. Here we see a stack implementation as in partial application. The top type alias declares a dynamic stack which is actually a tuple of two functions, push and pop. And the function declaration shows the implementation of this two functions, push and pop. And here we see the usage. As you can see, it does work like a stack as we would also expect it. And after creating it as an object, it is in the usage as actually the same as if I would use a class object, but it's just, yeah, I actually don't have a name for it. It is just an, yeah, applied tuple. So these are all very simple examples, but this code is actually in use now by apps I've written, by several apps by now. This is the store that keeps the state. So at the beginning, we have 5 type alias declarations for functions that give me access to the state, that let me change the state, that let me reset everything. This updated is actually a small pattern. It's the only pattern I use in the whole system, where I can, where it's a subscriber notification pattern. And of course, destroy would just, yeah, delete the file from disk and nil out everything. In the second half of the screen, you see, so the first half of the screen is a declaration, where the second part shows some of the implementation. The function that we use in here, they are, I have not shown them, but they are very, very simple function as well, and just would do that what they announced to do by their naming. Immutable data types. What cannot change on purpose also cannot change by accident, and which means a lot of errors and bugs simply cannot arise once the things that you're working on are not mutable. Is this readable on Zoom? Let us know. Okay. So this is now where it gets a little bit more exciting. I don't know how. Okay, guys on Zoom, you have the possibility to download my. Yeah, okay. Okay, what we see here is a coffee truck. By the way, I haven't got any coffee yet. This is from a project that sadly didn't go anywhere, but where a couple wants to create a second income for their family, and they want to operate a fleet of coffee trucks in the Netherlands. So what we see here is first of all, an immutable data type, and we know that it's immutable because all its properties are declared let. In Swift, that means after running the initializer, these values cannot be changed anymore. But of course, we want to reflect reality. Reality is changing, so how do we do that? At the top, we see a subtype called change. So it's a subtype. It's declared inside of coffee truck. So it's actually coffee truck.change. And at the bottom of the screen, we see the private alter function. So in the change enum, we have our, yeah, I call it vocabulary. defined where, for example, I have the commando opening it. It is just another subtype here. It's actually only used here to give it a real English vibe. It has no other meaning here. But if we now look at the right side at the top, we see how this is applied in our codes. So in the first line, coffee truck is created, and in the subsequent lines, I am altering it. So it means that I recreate the coffee truck object by actually creating a whole new object. And in the alter function, we see that on the left side, we have the command written out, and on the right side we actually connect it to an implementation, and we say, okay, for example, by closing it, it means that we will set the open property to false. By opening it, we will do this, set the same to true. By setting location to L, we will overwrite the location for the next iteration of the values. Yeah, at the bottom right corner, we also see the location definition. I just included it so that we can see that also this can be easily expressed in enums. And this is how we keep the state. So the app state itself is also immutable. It follows just the same approach. We have a change DSL, which we implement in the alter function, and in the upper right corner you see that we can have an app state, and by saying app state alter by setting current truck to T, we would now have T being set, yeah, as the current truck. And as you can see, the language that arises is very, very close to English. I mean, it is English, except for a very funky interpunctation, but I can promise you all my English has funky interpunctation. Here we have the implementation of a game that the older people, most of us in this room are older, I think. You know, from the good old Nokia phones, you remember the phones that you would only charge once a week? They had a nice game, and it looked like this. Do you remember? Yeah, so this game is encoded by the data structure that you see on the screen. Or this is not the whole game, it's the snake itself. And here we have, again, a change DSL, which lets the snake move or grow. And in the alter method, if we get the change value for grow, we call the move function, and as you can see, it's simply all the combinations of in which direction it is facing and where it's turning are simply listed and connected to the right implementation, where a new head coordinate is generated, a new tail is generated, and yeah, and it's determined in which direction the snake is now facing. So this is all the implementation we need for the snake, and I mean the game is not much bigger than that actually. Yeah, and this is a project that is actually very close to my heart. Does anyone recognize this board game? Yay! How many friends did you lose playing it? Yeah. This game is called Diplomacy. It's I used to play it with my friends in university. Usually 1 or 2 friends after that wouldn't talk to each other anymore. Diplomacy is a very fascinating game because it doesn't have any form of random chance, but only negotiation. You have to convince people to help you. You have to convince them that you will help them. And occasionally you just have to F them over. What I find fascinating about this example is the language that came out of this very little lines of declarations. So if you read the bottom block, it says, board execute command, move army of Germany from Berlin to Silesia. This is English. And it's exactly doing what it's saying. And for another reason, I find this example very, very interesting because this has been a coding cutter for myself during the last 20 years, which I would revise again and again to see how I would solve something like that today. And usually it would take a few hours, rather a few days to implement, for example, these movements as it's shown here. But in this declarative style, it only took me 17 minutes to write this. So declarative coding is much more efficient than what people mostly consider conventional coding. Yeah, this is probably very small now on Zoom. This is a small code from a smart lighting application. I myself have worked for 2 years in Eindhoven for Philips at the Philips Hue mobile team. And here I want to point out that that there are these small statements that we also can combine together. So the slide over there, before it's actually written back to the variable, but it's actually not shown here, all these commands will be executed and will be applied to it. And again, we see here quite big alter method that implements this vocabulary, where the left side lists all the commandos that are possible to describe in this system, and the implementation of these commandos. So how many people actually do have Swift experience here? I know you have Swift experience. Yeah, that's all. One thing I should say about the switch statement in Swift is that you have to have all cases for, I mean, I guess it's in most languages like this, but you have to, the compiler makes sure that you will implement all cases, and so it's a very secure kind of coding here. Questions so far? Some people have giant question marks in their face, like you? No? Okay. Okay. So the quiz was not the only assignment for you today. I want you to access this document. I gave you the bit.ly address so that you can type it easier. If you don't trust that I handle your access data correctly, you also can type the longer address. I'm not sure if the link on the program site is fixed, because that was pointing to an old version, my fault, but I'm not sure if it was fixed. So please take the address from this screen. Let's go through it. This data types here implement a to-do list. We have a struct called to-do item. And if we scroll down in line 32, we have the struct for a to-do list, which of course contains a number of to-do items, as we can see in line 41. The to-do list has 4 commandos: add item, remove item, and update item, and execute. Execute takes a function and just execute it, where the function will have access to the to-do list itself. This is only for this presentation, because this is how if we scroll down, we can see it, how we can actually do something like inspecting the to-do list and check if everything is as we would expect it, because in this playground we do not have unit testing. So this is like the poor man's unit testing in this case. But so you can use this, but it is usually not part of a data type. As we can see, so you can first of all ignore all the execute statements. That's why I shifted them to the right, so that they are more easily to ignore. The real commandos that we have here are this add item, A, Y, and K, A, J, and K. I, J, and K, yeah. Here's a remove. Here we have an update item. So how it is, how this works is that every item has an ID. And now if we alter J here, the ID will stay the same, and the order value will be replaced. So update takes one item, which is expected to be the new version of a previously available item. So what I want to do you to do now is to extend this to-do item or the list. And I am not a cruel pain in the ass. I have prepared things like to-do date, which is again an enum value, which has unknown, a date, or a time span. And the time span is also defined by me here. I offer directions or location, which again can be unknown, an address, coordinate, or directions. So what I want you to do is to implement something like a to-do date or an event location. Yeah, so is it clear what you have to do? Okay. I want you to extend the to-do item by, for example, adding a to-do date or a due date. The due date should be either of value unknown, of a date, or a time span. So you only need to add one variable to that. So in the section members, starting at line 12, you would just add, for example, location there. You could do the same also with the date, a due date. For what I also have prepared the, how did I call it? The to-do date enum in line 123. Yeah, the way you do it is you add a member, and at that point you actually can follow the warnings and errors of the compiler. It is quite good. I tested it also in this playground. But it also means, I mean, I also can tell you, so after you add a member, you need to add it to the private init in line 19. Then you need to extend the public init in line 17 for a default value. And after that, you can add a enum case to the change enum to change it. I would suggest you to do it in groups, especially if you have no experience with Swift. And I can come around and help you as well. So as you see, the output corresponds to what is executed in the execute commands. For example, this at the beginning, I check if the items are really empty. Then we add items, and then I actually test again if these items are found in the right order. Edit. You understand that? Is that clear? Is that answering your question?
Okay, so what you've demonstrated is fine. So when we make the changes, then we are to see new information.
Yeah, I mean, after you changed the to-do items or to-do list, you can add, for example, let's say, okay, let's do one together. I implement the due date. And actually now it also should start telling me that here is a mistake. As you can see, there is a very small red wiggly line indicating me that that there's a mistake. So so for the Zoom people in line 19, it tells me at the end that there's something wrong. And the thing that is wrong is that at the end of the execution of the main initializer, which is a private initializer here, the due value is not initialized. And that is not simply allowed in Swift. So, so how do we do that? We add a value to the call of the initializer. Okay, now it gives me another wiggly line because at this point I have to provide a default value to it. And as I am calling the initializers in the alter statement, there I have to pass in the now existing value as well. So, and by now it should be working again, though we cannot really use anything with the due date yet. But yeah, it works. I guess too many people are now compiling on this platform. So what is missing now is that we actually need to add a change case. We just call it due and we want to give it a to-do date. So this means that I also have to alter the switch statement in the alter function. But that is something that the compiler will always be able to tell. And now we return the new version like title. What was that? Completed. And now the D, which we have extracted from the command here. So now this is all we need to do. Or let's use an existing one. So for example, the K over here, or which one am I removing? Okay, the K. Yeah, we can first use a normal date. Distant future. This should be year 4000 or something. And if we now run it, yeah, it needs compiling. It's not Python. For example, it is now here. Is it visible? Yeah. Yeah, I included it from the beginning. I actually added it before we create the to-do list. So yes, it has to be there from the beginning. You said it's there at the beginning as well, and I would say yes, because if you look here, I added before we actually create the to-do list. I've already added it to the K value, so it is it is there from the beginning. Yeah, I mean, we could also say do it here, and then it would be replaced later. Of course, now I also should print it. Okay, now we see that it's visible in the last printed block. We have this date of 4000 of January 1st, 4001, where in the earlier versions it is set to unknown. So It was just very few lines of code that I had to change, and for most of it, I actually could follow the lead of the compiler. Yet I have I have added, quite quite interesting behavior. I can now express that a date is unknown. I can give it a date, what we have seen now, but I also could give it a time span. For example, like this. Tomorrow noon, and we want to last it for 2 hours. So, and probably I have to delete one more. So if you run it now, the date becomes replaced not by another date, but by a time span. And we can see here now the time span that says, okay, from tomorrow noon, and that it will be for 2 hours. So,
okay, it's obvious you're very comfortable
yeah.
with remembering, or the compiler is leading you to the properties that you have defined already for those. When you were first starting with Swift, what kinds of mistakes did you make? What was it like? 17 minutes to write a program. That's great, but that tech, you have evolved the technique to be able to do it in 17 minutes. For someone who's new to Swift,
I mean, this is not how conventional Swift looks like. This changed DSL stuff, I've seen it nowhere else so far.
okay.
Usually conventional Swift, looks a little bit more like Java. So as I said, I used this diplomacy cutter for myself, and in conventional Swift, I would need hours or days to do it, while this is very, very fast. And
Okay.
Of course, the question is how long do you expose yourself with a new?
Okay, from what you just said, you spent the time developing the abstractions of what each of these pieces of information represent, and then you created. Go back up to the top.
I mean, for example, if we look at the time span, which I haven't earlier. As you can see, it is just a declaration. There is no executed code involved. So I mean, that's also a way to describe declarative coding, that you have declarations and stuff, and the logic expressed as declarations and not as algorithm that is executed over time and changes the data.
So you took the time to take the abstraction of time and split it into these parts, and then the compiler led you to writing the expressions because it was following these declarations.
Yes.
Okay. So someone starting off then would be able to program quickly if they put the effort into declaring the components.
Yeah, the declaring of the components is the coding. There is no other step actually really involved.
Okay.
Do you want to try to add a location? I mean, the best way to learn is to do.
I personally have a feeling that you overestimate our Swift experience.
Yes, I just can say that I have tried this experiment with other people, and it's if you try, it's not taking you longer than 5 minutes. I've tried it with developers and non-developers, and yeah, the developers usually took longer because they were telling me that I was overestimating their abilities. But no, I mean, in the end, it is very simple. You just have to try. I can come around and help you, no problem. But I have tried it like with 6 or 7 people, and they all were able to finish it. We just have to try. So does anyone need help?
I have to say, before you started doing it on the screen for us, I was trying to work out what had to be done. And I have to say that the very first thing that you did shocked me. I would have never have guessed that. And that was that you did a let due date, or let due is to do due date or something. And I just didn't know where that came from.
So this line of code was the first one. I mean, that is pretty much standard Swift. This is a
okay. Yeah. I mean, I would never have known how to start that.
Yeah, that's why I'm here helping you.
Yeah.
So what we see here is a standard declaration for a member variable in a Swift object. We have 2 different kinds of, actually 3 different kinds, but we have 2 different keywords here. It's let and var, and let means that it actually not that it can't be changed once it was initialized, and var would be a variable that I can change afterwards. And since this is an immutable data type, we don't want the var a kind of a member property. Is anyone trying? Yeah.
So I got this first line you had there. I'm not accustomed to Swift, but apparently I know this pattern. But I tried the location.
Yeah.
The location is not a struct, it's an enum. So I don't know how to make a location instance.
You don't need to create an instance of an enum. Enums have cases. So you just use a case. It doesn't have to be created in any form. It's actually, it has a static behavior to it. Maybe I come and have a look.
Here, so I want to do something like this, but then with the location, but I put it up here because then it's an ID.
I mean, now you have, now it gives you the different kinds of location, the address, the coordinate, or the directions.
And what is this ID then?
Where do you see the ID?
Here, far ID.
I mean, that is var is yes, exactly. You don't need that. No, you don't set that itself. So for everyone in the question here is about the var ID declarations that you see in some of the enums. That is actually this var variable is actually more like a simple function that accesses the hash value, and you can actually ignore it. You don't have to set the IDs of an enum. It is generated on the fly.
Well, could you give us an example to create a location, Berlin?
To what?
The location Berlin, is that possible?
Okay.
City Berlin?
I mean, yes. So first of all, a location would be something like okay. I also have to check. So the address is enum. Sorry, a struct. So this one is instantiated. I don't know why it's not auto-completing the right init. Street, city, country. Okay.
Manuel?
Ja.
Ik heb een vraagje. A question from Huip Verwij. Manuel, can you show us how you create the graphics on the iPhone screen using your declarative paradigm?
Yeah, we come to that back later. We come to that back later, but I want to point out what I show is truly an architecture, meaning it is really independent from the UI. So none of the UI codes that you might see in my declarative example projects should be considered production ready. It is simply not what I'm focusing on here. But yeah, we come to that back later. So zip code is missing. So, so this is how we can create a location, and yeah. So I have now possibility to connect it to an to-do item because I have not done that yet, and I think we should move on. Okay, what I want to show you now is an architecture that is based on the things I've shown so far. It actually implements the so-called clean architecture by Robert C. Martin, also known as Uncle Bob. The main building block in that architecture are use cases, which I also group in features. Features are grouped into domains. Use cases have their own DSL, whereas features in one domain share a domain message DSL. This is how a use case looks like. There's a request coming in. It will be processed by an interactor. It might use some model type and gateways for that. Gateways being just dependencies as we know them from object orientation, and the result will be a response object. In the right corner, we see how I implement, how I declare a use case protocol in Swift. These are two example apps. Two example use cases. One of the left one adds items, where the right one removes it. They are pretty much identical, just that the request and the response DSLs are different, and therefore they do a little different stuff in the request function. Actually, this is the full-blown implementation. In this simple form, we could actually just ditch all the use cases and do the store operation in our features itself. But of course, I wanted to show this. This one is full-blown because this also allows any kind of asynchronous development that iOS or Swift in general offers. Then a feature is created like this. This is the complete feature implementation. There's nothing missing from this. So what we see is a feature that takes a store and an output and returns an input. And input and output both are simply functions that takes messages and does not return anything, as we can see in the first two lines. And then we create the domain by connecting all the features together. Here we have two features, a to-do list and a logging feature. For example, the logging feature doesn't take a output, so we also know it does not yell back to us. On the right side, we see the simple message DSL. The domain message DSL that that is being used here. So we have the messages to-dos initialized and the response to that initialized, and add and added, and removed, update and updated. And here is how we connect it to UI. In this case, this is an example for Swift UI. What we actually do here is that we have a view state, and that view state has a handle message function that we will inject as a receiver. Now it will get all the messages that are sent over the system, and we can react to that. I will not go much deeper into the user interface here because it's simply out of what we can talk in such a conference. If you go to my GitLab, you will find a lot of example codes, all of them with, or most of them with user interfaces. Again, the user interfaces are not meant for real life usage. They are meant to be simple, to demonstrate my stuff, not to be taken as a blueprint for your own apps. But before I go on, let's just go back to Xcode. I mean, also what I have to say, online playground, they are really nice things, but if you really want to code, nothing beats an IDE. It's much simpler to code anything like this in Xcode. So I've actually created my own version of what I just tried to make you do. And yeah, I will show you the user interface. Please don't judge me by the user interface. Please don't say this guy is crazy and we cannot give him any jobs, because the user interface is just meant to show that it's working. Down here, I have an add item button, and it will simply create one item with a nonsensical title. If I now open it, I can change it. Get coffee ASAP. And if I go back, it was immediately saved. I also can say, okay, now I got my coffee. Yeah. So this is the user interface. It is, of course, not very beautiful. But what I actually want to show you is the unit tests that I have here, because I think they are quite impressive. But let's maybe start with this one. For example, here we have what I actually call specifications. I think it's a better word than unit tests, but they can also be seen as unit tests, and they are always very similar. We create, we have the code that we want to test. In this instance, we want to make sure that the to-do item is set up correctly once we created it. And so this is a quick specification, and the matching language here is called Nimble. So quick and Nimble is a pair that always comes together, and it allows for this yeah, very straightforward testing. So the testing, as I do it, is always one interaction with the system, and then I check that every aspect of the system under test is actually what I would expect it to be. So just after it's created, it should have an ID, it should have the title it was created with, and it should have certain default values. And now I can actually change it, and I check the complete surface area that is available to me by this system again. And for example, I also check that. So here the title is changed, and I check that the title is actually not the same as the parent object anymore. But I also check that everything is not changed. So first of all, this gives you a crazy amount of unit tests if your company does count them, because every where is the Windows gone? Every it clause here is actually a unit test. So for this simple project, I actually have 165 unit tests. So and they are very, very easy to write. It takes me roughly a minute, not even a minute, to write one unit test in this approach. But it's more than that. If you look closely, you actually will realize this is testing on par with the scientific method. It is make one change to the system and observe that everything that you know about the system is still as you would expect it. This is, I call it the scientific method in action. Other questions about this testing? So this is, for example, for the to-do item itself. But for example, we also can test the whole app, the whole domain actually. This app has one domain, so app and domain are the same in this case. And we also, yeah, the screen is a little small. Yeah. As you notice that I didn't have to use before each in the other example. Here I have to use it. It actually that is actually because for the data types, if they are immutable, it's more or less calculated all at once, and we don't need this before each calls, but for the whole system they are needed because not everything is immutable in the end. The store is of course mutable. I think it's, this kind of expressing unit test is very powerful, but again, it is something one has to experience themselves to really appreciate it, like with everything in coding. I want to talk briefly about what I call axiomatic codes. I have mentioned it before, but not in this name. So I said in the alter functions, we always have on the left side in the case statements the vocabulary, and on the right side we connect this vocabulary to an implementation. And this is actually very similar to how an axiom in math works. I mean, 1 + 1 equals 2. We accept that this is an axiom, and if we say, for example, there is a finish command, then the completed member variable is set to true, and if there's an unfinished command, it is set to false. These are axiomatic statements in the sense that they are so simple that it's hard to imagine that there can go something wrong. This is what.
Hi there. There's a question in the chat from Gary Kapinski. Is it possible to derive the unit test code from the code to be tested?
I didn't get that.
Is it possible to derive the unit test code from the code to be tested by automatic unit test code generation?
I can imagine that could be possible, but I would say that it is a very dangerous thing to do because I mean that is actually tackling Kurt Gödel, and Kurt Gödel has shown us that systems of a certain size, and that size is not too big, need to have outside information to test their correctness. And if we would generate this outside information automatically, I would say we have not really tested. But that has nothing to do with how it's implemented, I guess. It's just, I would say, automatic test, having a system that writes your test automatically, I would say that sounds very, very dangerous. Yeah, we talked about this. Yeah, I want to just mention some of the properties very quickly. All what you would have to have in the end to deal with by this architecture is actually one function. So the whole domain is again only accessible to one function, which takes one parameter, the message. Cases of the message DSL. Therefore, it can be wrapped in anything. So it can also be used as a part of a system, as it can be hidden inside a class, a struct, or whatever. So yeah, it also is a great library architecture. It is truly independent from UI, which means it is also very portable. Yeah, it's easily testable with simple tests. I wanted to have easy and simple in one sentence together. And And what it does, and I don't have time to go deeper into that, it actually also allows teams to be much more agile again. And it actually allows that, for example, you create an app completely without user interface, and then the designers can expose themselves to that and develop a user interface for that, while nowadays often design comes first, and that's kind of a waterfall, and it's not really iterative and not agile. Yeah, I have here from Stephen's presentation 3 years ago, where he said where he had a conclusion. I totally say that yes, we are actually still thinking in many things like we are coding for 8-bit machines. So the first sentence definitely. The time that Stephen mentions in the second sentence as being 10 times faster, I would say yes, it's much more faster than that. If you compare several days working on a board game and 17 minutes, that's 200 times or something like that. I have to be cautious about sentence number 3, that managers will switch to declarative coding if they understand the benefits of it. In my experience, that doesn't work, because they are just so deep into sunk cost thinking that even when they explain it themselves, that they understand that they should change things, they are simply not doing it. I call that the economics of effort, that people are trained to think in effort thinking. I just have to spend enough time on something, and that will lead to some sort of value, and that is in engineering simply not true. If you don't have the capabilities, pushing around your variables will not get you any further. And that should be it. When will they finally switch? Actually, the best time is now, because of the economic situations, and that might be the only reason why teams change, because they need more from less money. Yeah, hoping for change without doing anything yourself is like standing at the train station waiting for a ship. Thanks.